All right, guys, let's go over 8.1 here. It says confidence intervals, the basics. It says a point estimator is a statistic that provides an estimate of a population parameter. The value of that statistic from a sample is called a point estimate. Ideally, a point estimate is our best guess at the value of an unknown parameter. So we're going to stick with a couple types of point estimates here. Okay. Usually we take a sample, and our sample mean is our best guess for the population mean. Or if we were looking at proportions, our sample proportion is our best guess for our population proportion. Okay, so our statistic is our best guess for the parameter. Our sample statistic is our best guess for the population parameter. Same thing over here. Okay, and in the context also of means problems, sample standard deviation is usually our best guess for the population standard deviation. So let's see what else it says. In each of the following settings, determine the point estimator you would use and calculate the value of that point estimate. Question A. It says quality control inspectors want to estimate the mean lifetime of AA batteries. Okay, so we're interested in mu because it's some sort of mean produced in an hour at a factory. They select a random sample of 30 batteries, okay, so that would be a sample size, during each hour of production, and then drain them under conditions that mimic normal use. It says here are the lifetimes and hours of the batteries from one such sample. Okay, so what we're asked to do, we need to figure out what the X bar is. So we need to find the average of these. Okay, guys. And the way we can do that is in our calculator. So if I go into my stat and then edit, I can enter this data into list 1. So that's what I'm just going to do. 18.83, 16.22, 17.58, 16.59, 15.84, 17.13, 17.42, 17.10, 17.65, 16.96, 16.63, 16.40, 16.84, 17.35, 15.63, 16.37, another 16.37, 15.98, 16.52, oops, I forgot one. I got the 15.98, now I'm up to 15.80, 16.52, 15.93, 17.04, 15.81, 17.07, 17.45, 15.73, 16.85, 16.74. What I might do, I just might quit out of there, and I just might do a sort ascending, okay, for list 1 where I have my data. Now, why would I do this? The reason I would do this is to kind of check to make sure I didn't make any transpositional type of errors, like forgetting a decimal point or something like that. So if I forget a decimal point, it's going to throw the mean way off. Okay. And also, this is the last data point I have, and it tells me that's the 30th data point. So it's a way to verify I got everything. Okay, so we can quit out of there, and we can go stat, calculate, one variable stats. My data is in list 1. There is no frequency So I can delete that and just calculate. So here we go. The mean is 16.70. Okay, and this has units on it, it's hours. So this is our best guess for what mu would equal because it's from a sample mean. Okay. That would be our best guess of the mean lifetime of each battery, or the mean lifetime of the batteries coming off the production line that particular hour. All right, now let's look at question B. It says, what proportion of U.S. high school students smoke? The 2007 Youth Risk Behavioral Survey questioned a random sample of 14,401, okay, so that's my sample size, students in grades 9 to 12. Of these, 2,808 said they had smoked cigarettes at least one day in the past month. So because this is coming from a sample, that's a p hat. So 2,808 out of 14,041 said they had smoked. Let's get a decimal version of that. And it looks like if I round it, it's about 0.200. Okay, that's what that says. All right. So our sample proportion is about 20%. Okay, that would be 20.0%. Okay. And that's our best guess to what the true population is. True population proportion, which we call rho. So that's what they're asking for. Okay, now let's go on to the next part. It says a confidence interval for a parameter has two parts. An interval calculated from the data, which has the form estimate plus or minus, this is the point estimate by the way, okay, plus or minus some margin of error. It says the margin of error tells how close the estimate tends to be to the unknown parameter in repeated random sampling. And number two, it says a confidence interval, which gives the overall success rate of the method for calculating the confidence interval. That is, in C% of all possible samples, the method would yield an interval that captures the true parameter value. So this is kind of difficult to understand, so I'm going to try to explain what this means. Okay. So let's just kind of think back to sampling distributions real quick, at least for means. Okay. If I looked at a sampling distribution, and let's just say it's normal, we know that the true mean, both the mean of the sampling distribution and the mean of the population fall right there. They fall down the middle. Okay. But my x-bars vary. Okay. My x-bars vary all over the place. Okay. I'm just drawing in the x-bars here, or writing in the x-bars, so you know that any individual sample mean could be different than the true population mean. So here's the idea of a confidence interval. Okay. What I'm going to do is I'm going to take a sample and get a sample mean. So I'm going to get an x-bar. The problem is I don't know which x-bar I'm getting. I could be getting the x-bar that's really, really far away from the true mean. Right? I mean, hypothetically, we could. Or we could be getting an x-bar that's right in line with the true mean. So what we have to do is we have to take our sample statistic, or our point estimate, as it's known, and we have to add some sort of slack. Okay? And we call that slack the margin of error. Okay. Because I don't know if this x bar is really close to the population, I need to take this x bar and I need to go a certain distance to the left and a certain distance to the right. And hopefully by going a little bit left and a little bit right, now that gives me an interval that I feel pretty confident that somewhere between this lower number, wherever it falls, and this upper number, wherever it falls, I'm going to capture the true population. Okay, that's the idea. If I go down a little bit and I go up a little bit, I'm pretty confident that somewhere in that space or somewhere in that interval, the true mean is going to fall. We don't know where it's going to be. We don't, because hypothetically, we don't know if we're getting a higher mean than what's the true mean, a higher sample mean than the true mean. So, okay, when we make this interval, all we're saying is we have some degree of confidence that the mean would be anywhere from here all the way up to there. Okay, because we don't know if this x bar is on the high side or on the low side. Okay, so the mean possibly could be there. It could be here. It could be there. It could be all the way up to the ends of the interval. Okay. So that's the whole idea of a confidence interval. We can be assured that we have a certain level of confidence that the true mean falls within that scope. Okay. So, going back to the note card. Here is an interpretation sentence that you should try to remember. Okay. So what's the meaning of a confidence level? In repeated samples of the same size from the same population, approximately blank % of the intervals created would contain the true proportion or mean, depending if you're talking about a proportion or a mean in the context of the problem. Okay, so these sentences are important to remember in how you interpret a confidence interval. And the confidence interval itself, here's something to remember: we are blank % confident. Okay, so for example, if I use a 95% confidence interval, we would say that we are 95% confident that the interval from the lower limit to the upper limit captures the true mu or rho, okay, in the context of the population. Okay, this will make more sense as we do some of these problems. Hopefully, that's the goal. All right, so this first example here for a confidence interval. It says in late 2009, the Pew Internet and American Life Project asked a random sample of 2,253 U.S. adults. Okay, so right away, I know that's a sample size. Okay, so as I'm reading these problems, I just kind of like to highlight the numbers. It says they asked them, do you ever use Twitter or another service to share updates about yourself or to see updates about others? It said of the sample, 76% said yes. So what we have there is we have a p-hat. P-hat is 0.76. It says, according to Pew, the resulting 95% confidence interval is between these two values. Okay. Well, we're going to interpret this in just a second, but how did they come up with these numbers? See, the thing is, 0.76, the way they came up with this numbers is they took p-hat, which is our point estimate from our sample statistic, and they added or subtracted a certain margin of error. Okay. That's what they did. So I know that the p-hat was the 0.76. Now how could I figure out what the margin of error they added was? Okay. Well, if I were to subtract the margin of error, I would have got 0.732. If I were to add it, I would have gotten 0.794. Okay, so if we just look at, adding the margin of error, that would give me 0.794. If we do some basic algebra, margin of error there is 0.034. So they added 3.4% on both sides. Okay. So I don't know where the true row is. I'm not sure where it is, but it could be anywhere between 0.732 all the way up to 0.794. So the true proportion in the population that use social media is between 73.2% and 79.4%. It falls somewhere in this interval. Okay, it could fall anywhere in that interval. And we have that much confidence in saying that. So how would I interpret this? Here's a sentence we would write. We are 95% confident that the interval between 0.732 and 0.794 represents the, instead of saying captures, I'm using this sentence right here, represents the true population proportion, and I'll even give the proper symbol, row, okay, of US adults who use Twitter or other social media sites. So in this particular one, we didn't have to do a calculation. They just wanted us to interpret what this interval really means. Okay, so my row it's got to be somewhere between here, between 73.2% and 79.4%. Could be as low as this, could be as high as this. Okay, because our p hat, you think about it, when we look at a sampling distribution, here's the true one, but our particular sample could be higher or lower than that, our sample proportion. Okay, so in order to capture this number down the middle, okay, we have to go a certain distance to the left and a certain distance to the right. But we don't know whether we're getting the low side or the high side. That's why we have to add and subtract. Okay, because we're only getting one p hat. We're not taking a whole bunch of p hats. All right, we're only grabbing one, so we have to go a certain left, certain distance left, and a certain distance right. There's a trade-off. Okay, the more confidence you have, okay, if you want a 99% confidence, your interval would become wider. Okay, the more confidence in your answer you want, this interval gets wider. The less confidence, the interval shrinks, it gets smaller. Okay, that's a big idea there. So going on to the back page here, it says before we calculate a confidence interval, we have to make sure three conditions are met. So before we do calculations, three condition check. Random. Your data comes from a well-designed random sample or a randomized experiment. Okay, so we're looking for keywords like SRS, simple random sample. All right, is the sampling distribution normal? Okay, so does it meet the large counts condition for proportions, or does it meet the central limit theorem for means, or are you given that the population is approximately normal? And lastly, does it meet the independence or the 10% condition? Okay, that applies to both proportions and means. All right, the population has to be at least 10 times larger than the sample size. So this example, it just says, check that all conditions are satisfied. So it says Mr. Vignoli's class wants to construct a confidence interval for the proportion, row, of red beads in the container. The class's random sample had 107 red beads and 144 white beads. All right. It said Mr. Vignoli informed the class that there are 3,000 total beads in the container. Okay. So these are the only ones they drew in their sample. Let's add those together. Okay. If we add those together, 100 plus 100, 200, 44 plus 7, 51. So there's 251 total beads in the sample. Okay. So what would our p hat be? Our p hat would be 107, because we're talking about the proportion of red beads over the total, which is 251. We'll get a decimal approximation for this, which is about 0.426 roughly. Let me just store this proportion as A, just temporarily. Okay. So let's check the conditions. Random. Okay. It says the class's random sample had 107 red beads and 144 white beads. So it tells us in the problem. So I can simply write here random sample stated in problem. Now let's do an independence check. Okay, so our sample size was 251. Our population size, we were told, was 3,000. Okay, so is n greater than or equal to 10 times little n? All right. So if I just work out the math here, 10 times 251 is 2510. Okay. So that checks out. 3,000 is bigger than 2510. Okay, and the last condition is the normal condition. Now, when we use this for proportions, we say n times rho is greater than or equal to 10, and n times 1 minus rho is greater than or equal to 10. But I don't know rho. So what we have to do here, instead of using rho, okay, we actually have to use p hat, because that's going to be our best estimate. Okay, that's going to be our best estimate. All right. So here we have 251 times p hat, which is 0.426. If you notice here, okay, if we were to just multiply here, it would just give us 107. So 107 is greater than or equal to 10. All right. And basically this number plus this number is going to add up to whatever n is. So this next one is going to be 144. It's greater than or equal to 10. Or if you don't believe me, you can run it. That's going to be 0.574 if I take 1 minus 0.426. If I multiply those together, it's going to be 144. It's going to be the number of white beads. Okay, so that's bigger than 10. That's bigger than 10. So the random condition is met, the independence condition is met, and the normal condition is met. All right. So all three conditions are met. So eventually we could calculate the confidence interval. And we'll learn how to do that in just a bit. And this question was just asking me to check the conditions. These are the conditions that have to be checked before you can do calculations. This really isn't a calculation. Okay, that's just basic. And I think that's pretty much it for section 8.1. So thanks for watching.